This is the one, the only case here. So he's going to be talking to us about different title than what I have on the app here, but hydrogen bonding essentially. So go ahead and take it away.
Thank you, Dr. Okay, so thank you for coming, everyone. Thank you for being so interested in my life outside of this presentation. So in Dr. Jim Phillips' lab here at UW Eau Claire, we study hydrogen bonding in a lot of different complexes from like a physical chemistry standpoint. My personal project are various Fluoropyridine-HBr complexes. So here's a depiction of 3,5-difluoropyridine. So just a little introduction, just to kind of like lay the groundwork for everything I'm going to talk about. So what is a hydrogen bond? I'm guessing everyone here is chemistry people, so I'm sure you've all heard of hydrogen bonds. Basically, interaction between partial positive on a hydrogen and a partial negative on another electronegative atom. In general, we are taught in like Gen Chem that the donor and acceptor atoms can only be like nitrogen, oxygen, fluorine. In reality, they can be a wide range of atoms with varying electronegativities. Something interesting about hydrogen bonding is that we're always told it's like a intermolecular interaction, but because of the geometry and the, as we'll see later, the covalent character of a lot of these interactions is not purely electrostatic in nature like you would expect from, like, for example, this interaction is not purely just a dipole-dipole interaction. Another interesting thing is that it's the first step in acid-base chemistry. So here is the autoionization of water. You see, you deprotonate a water and protonate another water, you get hydroxide and hydronium. You can imagine that at some point in this reaction, you will have something that looks like this, and that is no coincidence. Hydrogen bonding explains things like the physical properties of stuff, such as water, high boiling point for relatively low molecular mass, structure of biological macromolecules, DNA, you have hydrogen bonds connecting, or at least partially explaining the connection of the two helices. And just also, we're going to talk a lot about infrared spectroscopy. So IR photon hits a molecule, if it's the right energy, it will excite that bond and cause a vibration motion. Okay, background. So for the past like 50 or so years, there's been a whole slew of ways of studying hydrogen bonds and like small molecule complexes like this. A lot of the studying has been done on like R3, NHX complexes, so alkyl groups and halogen acids. In general, the thing observed is that extent of proton transfer increases as R becomes more electron donating, so stronger base, and then X becomes larger, more stable conjugate base for the halo acid. So we've previously studied NHCl systems, so like ammonia HCl, acetonitrile HCl, fluoropyridine HCl. So just some summaries from the fluoropyridine HCl work, because it is so similar to what I'm going to be talking about. So addition to fluorines around the ring, changed the strength of the complexes. Positioning was really important. The HCl stretching band in the IR spectra paralleled the fluorine substitution, so basically the frequency of that band decreased with a stronger complex. Stronger complexes shifted the proton transfer structures in simulated solvents. We'll get into that in the computational side of things, but weaker complexes didn't really change that much depending on the environmental factors. So bonding analyses were effective in predicting proton transfer, and we're going to talk about Fluoropyridine-HBr. So just a little bit about our methods. On the computational side of things, we do like quantum chemical calculations, specifically density functional theory. So there are like different ways to do quantum calculations. There are like wave function type methods. We do something that, you know, you can imagine if you have like a nucleus and it's orbiting electrons, you don't only have to account for the electron-nucleus interaction, you have to account for all of them interacting with each other, and that is a pain. So DFT, density functional theory, treats it as one electron cloud and uses that to predict structure. Basically, it makes small adjustments to the electron density, which changes the molecular structure, which gives you the lowest energy structure, and the supercomputer kind of plays with that until it gets like the global minimum. It also predicts like the frequencies that we will see in the spectrum. So our experimental methods, because we kind of do experimental and computational stuff, we do low temperature matrix isolation infrared spectroscopy. So just breaking that down, low temperature, we do anything from 6 Kelvin to 20 Kelvin. It's pretty cool, because literally pretty cold. Matrix isolation here is an atomic description of that. Essentially the idea is that you have like a fairly inert host, which we use like neon and nitrogen, and then you have the guest, which is the thing we care about, which essentially gets trapped in little like cage structures made by the solid host condensing at those low temperatures. Infrared spectroscopy, I already talked about that, it's vibration stuff. Okay, so into the actual results. I chose a series of the complexes we studied intentionally. So here's just pyridine-HBr. We see that you have a really short NH bond, a really long HBr bond, and a large negative charge on the bromine, pretty large binding energy for a hydrogen bond. So we can confidently say this is more of like an ion pair or proton transfer structure. You add a fluorine at the 2 position, it withdraws a lot of electron density from the nitrogen and turns it back into more of a hydrogen bonded situation where you have like a smaller charge in the bromine, a longer NH bond. You add 3 fluorines at the 3, 4, and 5 position, you actually end up with a very similar structure to 2-fluoropyridine, even though you have 3 fluorines here and 1 here, so that really highlights the influence of like the positioning of the fluorine. Also, you see some electrostatic repulsion between the fluorine and the bromine here, which gives you like 2-fluoropyridine as the only like bent structure. Finally, we have the weakest complex here, which is pentafluoropyridine. Those 5 fluorines are just withdrawing so much electron density from the nitrogen. You have this very, very long, weak NH bond. This is like totally hydrogen bonded, very low extent of proton transfer. Another thing we study is matrix effects or media effects, environmental effects. So this is kind of a computational representation of that matrix thing I showed you in the lab, or matrix isolation I showed you a couple slides ago. So here I chose to talk about 3,5-difluoropyridine, 2,6-difluoropyridine. So isomers, but as we talked about already, the placement of the fluorines is important. You see that 2,6 is weaker, 3,5 is stronger, and is closer to proton transfer. So you crank up what is called the dielectric from dielectric 1 gas phase to dielectric 3. You see some pretty significant changes in the structure. So 3,5 was already strong enough that it was pretty close to proton transfer. You see these NH and HBr bonds are a lot closer in length than for this complex. And amazingly, such a small change in the dielectric constant is enough to transfer 3,5-difluoropyridine to a proton transfer structure from a hydrogen bonded structure, while the dielectric constant, the environment being the only thing that we changed. Since 2,6-difluoropyridine is a weaker complex, it was not close enough to proton transfer for that dielectric to be meaningful. However, you do see a slight contraction of the NH bond compared to the gas phase. So onto like predicted spectra stuff. So the main frequency that we look for in our IR spectra are the actual HBr bond itself, because it changes significantly from the free hydrogen bromide stretching motion to one that is like in that complex that I have diagrams of earlier. So this is a representation that if we set free HBr as like a 0 set point, as you have complexes with increasing strength, this is how much the IR band frequency shifts. So normally free HBr is like 2700. You get stronger and stronger. You can actually shift that all the way to something like 1600 in the predicted stuff for strong complexes. And just to be clear, like dielectric constant changing is a simulation of the different host gases from the matrix isolation. So like neon has a approximate dielectric constant of 1.2, nitrogen is weird for a lot of reasons, but approximately 1.5, 1.6. And here are our actual spectra. So I chose like just the most interesting regions to talk about. So once again, we're talking about 3.5 DFP and 2.6 DFP. So this bottom spectrum here is just the HBr spectrum in neon. Here is just the 2.6 spectrum in neon, and here is both of them being deposited onto that very cold surface at the same time and mixing hopefully homogeneously. And you can see that there are a lot of characteristic bands that you would expect because you're going to have a lot of free HB or free 2.6 DFP in the combination spectrum. But you also see it as this like big new thing, which is definitely new. And so we can pretty confidently say, after doing a lot of dirty work to like assign other bands and making a case for why we think this is the HBr stretch, we can be pretty confident that this is the hydrogen bond infrared spectrum, which I think is pretty cool because normally when you like study infrared, you do it in like organic lab and you're like, oh, 1700 wavelengths, there's the carbonyl, like great, it never changes basically. But as you can see, this is still 2.6 difluoropyridine, but now in a nitrogen host, and it just looks totally different. It is like this super broad, just ugly looking product band, which is a nightmare to assign. 3.5 difluoropyridine, it's a much different story in the spectra, but the idea is the same, that you have these brand new product bands right there and right there, right there and right there. And it really, like the difference is the fact that this one is there in neon and not there at all in nitrogen really tells you how much of an effect that the environment is having. So just some conclusions to wrap things up. Position of the fluorines in the pyridine ring is very important for determining complex strength and HBr frequency shift. Complexes, an interesting comparison to the HCl data, even pyridine HCl, the strongest HCl complex, did not predict to have proton transfer in the gas phase, but pyridine-HBr does have proton transfer in the gas phase, which speaks to just like how strong of an interaction is, because you have that stable conjugate base bromide and you have still a fairly strong base in pyridine. So we again predicted proton transfer increasing as you increase the dielectric constant, and our hydrogen bond-like spectra were observed for weak complexes, and proton transfer-like spectra were observed for intermediate strong complexes. I didn't really show those spectra, but what that means is like the H-bond-like spectra has that one distinct kind of broad like HBr stretching band, whereas proton transfer-like spectra, you can imagine you aren't really going to have an HBr stretch if the base has deprotonated the acid, and that kind of like splits and gets like coupled with other frequencies and becomes very difficult to work with. And the HBr stretching frequency changed dramatically from host to host, changing the host matrix or changing the dielectric constant. That is all I have for you. These are my references, and I'm glad to be at NCUR and glad to present for you all. Thank you for listening. Are there any questions I can answer? Yes.
So in your in your computational setup, there were like two selections you had. There was like I think it was opt, tight, and then yeah. So what are those two, and then the int ultrafine? Like what do those two do?
So opt equals tight means that like the So you can imagine when we're like optimizing a structure by shifting the electron density, shifting the molecular structure, trying to get that lowest like energy structure. Opt equals tight, as I understand it, is placing like pretty stringent requirements on like what we consider the lowest energy structure. NT equals ultrafine. You can imagine that because this is running on a supercomputer and it's doing so many of these modifications to the structure and the density, that you kind of like take it in one direction, oh, then increase the energy, take it in the other direction, oh, now it's decreasing, keep going in that direction. You kind of have to like readjust until you get that equilibrium low energy structure. So N equals ultrafine, I believe, is referring to the step size of those changes. So that's referring to a lot of steps being gone through in order to have like a very like nuanced approach to that lowest energy structure. So we're like confident in it. You in the back?
How much clock time does it take to get like the full result?
So it can take a long time. Partway through our research, we switched from a weak supercomputer to like a much more powerful one, where we can devote like we do like 96 gigs and 24 processors for computation. And obviously, like the things we ask for in our files change the computation time. But if we just go all out and do like the bonding analysis, structure optimization, frequency predictions, and like potential energy curves of the bonds, you're looking at like 6 hours at the least. It can take overnight easily. Usually I run like all of the complexes at the same time, and